I hope all of you will be fine. So today we are going to discuss the series diode configuration of the diode as we are going through. So in this lecture we will discuss the series configuration of a diode for any power supply. Initially we will discuss the basically DC power supply, and after it we will go to different power supplies and different configurations of diodes. So as your midterm is coming around, I want to tell you that you should get prepared for your midterm, and all the lectures including the all the lectures including all the things which we have covered in our classes before the online lecture will be included in your midterm examination. Okay. So let us start today's lecture. It is about the series configuration of a diode. So if we connect a diode with a power supply, DC power supply, in such a way that the anode of a diode is connected with a power supply and cathode is with a resistor in such a way that there is only a single way of a current, you can see that current can only be passed through in this direction. So this is called a series diode configuration. In this way, in this configuration you can see that the positive terminal of a voltage source is connected with the anode of a diode. So that's why this is called a forward bias configuration. Okay, in this bias configuration, the you can see that in this way, in ideal situation, this diode will be considered as a short circuit. If we are considering it an ideal condition, it will basically be a short circuit. Okay, sorry for my drawing again. This is a power source. This is again R. This is E. This is E. So how can we calculate the value of this current? We just have a single voltage source, a single resistor. So the value of I can be easily calculated as I is equal to E by R. It can be calculated by this formula. Sorry for my drawing. Okay, it can be calculated by this formula, and the value of VR in this case will be equal to IR. Okay, the current is known. I have already told you that there are basically three quantities concerned with any component, any electrical component. What are those quantities? Those are basically the voltage, current, and the resistance or impedance of any component. So if any two of them is known, you can calculate the third one. Okay, if any one is known, then you should have to find the second one so that the third one can be easily calculated. In this way we have two quantities, so VR can be easily calculated here. Okay, this is the ideal scenario. If this is not the ideal scenario, that we have now here the silicon diode. It is written here that this is a silicon diode. So every silicon diode has some potential drop across the diode in the real scenario, in a real world scenario. So in that case, VD will be equal to 0.7, and for germanium case, that would be equal to 0.3 volts. Okay, so if this is the what is this? This is if this will be the silicon, so I can draw it like this voltage source here. Okay, and this in silicon, this voltage source will have a value 0.7 volts. Okay, recently in previous lecture you guys have seen that in any diode current, in any diode circuit, in any diode curve, the conduction of a diode only starts after a certain value, this one. Okay, this is basically the value. in which the diode conduction start. For the silicon, this value is zero point 0.7. This is the knee voltage, and for germanium this value is zero point 0.3. So we can write it like this one. If this is not the ideal scenario, it will be modeled, this diode will be modeled like a zero point 0.7 voltage source, and it is written here. For analyzing the diode, we can write it. We can, okay, for the analysis purpose, the VD is now considered zero point 0.7 volts. And here, if you apply the KVL, you can find that the value of VR will be equal to E minus VD. Okay, if this is VR, this is, let's say, this is plus, this is minus, this is plus, this is minus, and this is VR. This is again the voltage drop. This is VR. If you apply KVL here, then the equation will be E equal to E is equal to VD V of D plus V of R. Okay, so now you can see that this is the equation, because now here this is voltage rise, this is voltage drop, this is voltage drop, because now if you consider this current, here the current is entering through the negative terminal and coming out of this positive terminal. Similarly here, if this in this clockwise direction current, the current is moving into this positive terminal and coming out of this negative terminal, so this, that's why this is the voltage drop. Similarly, across the resistor, it would always be a voltage drop. So that's why we have written it like this, and from this equation we can calculate this one. Okay. Similarly, the value of ID is equal to IR is equal to I of t. These are basically the three currents which are basically same in this series configuration, and the value of it can be calculated by the voltage drop, which we have calculated here, VR divided by the value of this resistance. So by this we can calculate the value of I of t, and this is the same. Actually, the series current is same, so we can analyze this series diode configuration like this one. Similarly, if we have more than one diodes here, let's say we have another diode here, and let's say we have another diode here, and we want to analyze it again. What will we do? We will just model it. If this is, let's say, silicon again, if this is not the ideal condition, what will we do? We will again model. We will again model another voltage source, and then the resistor. Okay, this voltage source will have a value of zero point 0.7 because we are using a silicon diode now here. So if this is the scenario, we will analyze it accordingly. Okay, so in this way, the diode configuration will be used to find the current and many other things. That is why I delivered a lecture on series circuits in our first online lecture. Similarly, I have covered the basics of electric circuits, which included the series circuits, parallel circuits in our face-to-face classes. So the reason I have covered all those previous concepts is to analyze the circuit like this one, and these concepts will also be used later on. Okay, so let's move on. Okay, if we have a configuration, uh, if the diode is reversed bias, so if for reverse bias, the anode of a diode will be connected with the negative negative terminal of a voltage source, and the cathode will be connected with a positive terminal. So it, in ideal cases, it will behave as a open circuit. So it will become like this one. It will be the open circuit. It will be the open circuit, and now as it is the open circuit, that's why the value of current will be equal to 0. Okay, the value of id will be equal to 0 because there is no way for a current to flow in this circuit. Similarly, as there is no current here, you can see that the value of ir is 0. The value of ir is 0. This open circuit had made all the current equal to 0. There is a supply here, and all this supply is basically dropping here. If this is E and this is the voltage Vd, so all of this Vd will be consumed here across this open circuit. This is the core electric circuit concept which you guys have developed previously. So if IR is equal to 0, the value of VR, which is equal to IR into R, this will always be equal to 0. So this is basically the reverse bias case, because in reverse bias case, in ideal condition, this will behave as a open switch. So that's it. So let's move on. Basically, this is a question related to the previous material which we have done, and in this question, what is it asking? It is saying that for the series diode configuration of figure 2.13, this is figure 2.13, determine VD, VR, and ID. Okay, so this is a silicon diode, so the value of VD in this, initially in this question, you have to see whether the voltage here is uh, strong enough to make this diode forward bias or not. Okay, so as this is 8 volts, and you know that the value of 8 is greater than zero point 0.7. This is greater than zero point 0.7, that so this voltage will drive it in the forward bias region. Okay, if the value of the applied voltage to the diode is greater than the knee voltage, so it will drive it into the forward bias region, and you will be okay to find the current. Otherwise the current will be equal to 0, because if the value of the applied voltage, this is the curve, if the applied voltage is somewhere here, and this is the required voltage which is zero point 0.7, after it will try to conduct the current, and if you are applying any voltage here like zero point 0.2, so below zero point 0.7 you can see that there is no current conduction here, and it will block all the current here. If the value is greater than zero point 0.7, so it will try to conduct the current, so it is conducting here, so that's why the value of Vd is equal to zero point 0.7 in the conduction region. Similarly, you know the formula of finding the Vr is equal to E minus Vd by KVL, and by subtracting the value of 8 zero point 0.7 from 8, it will become 7.3, and similarly the value of IR is equal to VR by R, and it is 3.32 milliamperes. Okay, so that is the example number 2.4. Let's move on. Parallel combination. The parallel combination of a diode is again very important. When two or more diodes, similar diodes, okay, if this is the if this is the silicon diode, so this should also be the silicon diode in parallel combination. You can see that the both the ends of the of a diode are connected with each other, so that's why this is basically a parallel combination. So if these are connected in a parallel configuration, what will be the analysis procedure? You can see that in a conduction point of view, the value of VD will be equal to zero point 0.7 across both the diodes, which is written here. Okay, this is the as both are the silicon diodes, so the conduction voltage will be zero point 0.7. The value of what is the value of V of R? How can you calculate the value of VR? Just by applying KVL here. If you will apply KVL here, what it will be equal to? It will again be equal to E equal to VR plus V of D. Okay, so by this formula you can write the value of VR equal to E minus V of D. Okay, it is from where we got it. We applied KVL here in this loop. In this loop we have applied KVL, Kirchhoff's voltage law, and after finding out this equation we have rearranged it to find the value of VR, and now the value of VR will be equal to 10 minus 0.7, and this value will be equal to this one. Okay, the value of VR is this one. Similarly, what is the value of I of R? To find the value of I of R, we have to find the voltage drop across R and then the value of R. So the voltage across R is V of R, and we have calculated it already. That is 10 minus 0.7 and divided by the value of R, that is 0.33 kilo ohm. So we have found it again. So this is this current. This one is the current here. This is, let's say, I1 or IR. I1 is here. This current will be moved toward this diode. There are two diodes here, and as the two diodes are similar, so equal amount of current will be distributed in each diode, and both are same diodes and having similar configuration, so both diodes will conduct the same amount of current, which will be the half of the initial current value, because both are same, because both are the same values, so it will be divided into two, and half will be conducted in half will be conducted by this diode, while remaining half will be conducted by this silicon diode, and you will have 14 milliampere flowing through each of the diode. So that is the configuration, and this is the mechanism to find the voltage of currents and voltage in this circuit. The important question here is that what will be the value of V naught? V naught is the output voltage, and what will be the value of V naught? Can you guys find it out? What will be the value of V naught? Okay, can you guys find it out? It will be equal to the value which has been developed across this diode in a conduction region. So that will be equal to V naught will be equal to VD. Sorry, this would be equal to V of D. And what is the value of V of D? In silicon diode, the value of V of D is 0.7. Okay, so the value of V naught here will be equal to 0.7. If it is asked from you to find the V naught as well, so you can find it from this equation as well. And the value of this current, what will be the value of this current? As all the current which has been flown from here has gone here and here, so there will be no current left out to flow from this region. So the current here will be equal to 0 unless and until some resistor is connected here. If you will connect some resistor here, So the value of this current will be changed and will have some value. How would you find it? You would find it by using any feasible current divider law. Okay, you will find it by using the current divider law, and we will discuss it later on. Up till now, this thing is enough. So this is the forward direction current movement, etc. Let's move on. This is another example. Kindly have a look at this example. This is example 2.11 in your book. Kindly take a look. This is a very interesting example because you have now two LEDs. One is red and one is green. You are both are biased. And for LED, if this is gallium arsenide LED, so both have different voltage level, and for forward direction, it will behave as a 2 volt source. And as you can see that this is connected in reverse bias, it is connected in a reverse bias condition, so it will behave as a open source. Okay, how would we calculate the value of 20 milliampere? All is written here, and kindly please take a look over it. Over here, it will be of great help for your exams. Let's move on. Okay, the next thing which is very important is the rectification of a diode. What is mean by the diode rectification? What is a rectifier? Rectification is the most widely used application of a diode because it allows current in one direction and blocks it in another direction. So that's why rectification or alternating current to the DC current conversion is very important, and it is the most important application of a diode. So what happens is here, in rectification, the alternating current AC waveform is applied here. For the AC waveform, this positive cycle will be conducted by this switch, because in this for this cycle it will be this terminal will be positive while the other terminal will be negative. So for this configuration, this diode will behave as a short circuit as written here, and it will conduct this waveform. Okay, the positive waveform will be positive wave will be conducted by this resistor, and so V naught will be equal to Vi, and it will be like this one. For the second turn, when the second cycle arrives, the polarity of the input terminals will be reversed. It will become negative, it will become positive. As this is the negative waveform, so it will be negative here. For the negative or the alternate polarity, this diode will behave as an open switch as written here, and there will be no current or no voltage here. And if the same is again applied here, same waveform is again applied here, so the waveform will become like this and again zero, and so on. So in this circuit, you can see that it was basically a the waveform which was basically flowing in both directions. But here the waveform is in this one direction, and in another direction there is zero voltage or zero current. So that's why this is called the direct current. Later on, we can make any more other configurations that we have discussed in our class, that we can write, we can use the we can use here a capacitor. Sorry, we can use here the capacitor as a filter to remove the ripples. So what will happen, it will move and then it will go here, it will move and then it will go here, and at the end, by using the complete filtering, this will already be used. This will be like this one, this waveform, and this is called a DC waveform. Okay, so the why we have seen here, why we have seen just it here and not the capacitor, because this is the application of a diode. By using other circuits, we can see the direct current conversion of this circuit later on. Okay, so this is basically the current waveform, and voltage waveform will always be like this. Sorry, this is the voltage waveform, and current waveform will also be like this one. The value of this, the average value of this wave will be equal to 0.318 vm. Okay, how can we calculate it? There is a formula to find this one, that will be 1 over uh, 2 pi 1 over 2 pi and integration from 0 to pi Vm sine of omega t d omega t. Sorry, d omega t. Okay. What is V of M here? Vm is basically the peak value of this AC current, which is this one. Okay, it will rise, and at there is a time when it will move towards the peak of this voltage form, and that is this Vm. What is omega? This is the frequency of this waveform. As you can see that the AC waveform in our houses have the frequency of 50 hertz. So that omega basically is omega equal to 2 pi f. Okay, and f will be the frequency. After the mathematical conversion and mathematical calculation of all this, you will see the value of this 1.318 for this half wave rectifier. Okay, so this is the formula which we have to see. PIV, peak inverse voltage, this thing is very important for the rectifier. Why is this important? Because for the forward direction, the diode will be in conduction state, and it will behave as a short circuit. Similarly, if the diode is not in the forward bias region and it is in reverse bias region, so all the voltage here will try to break this region. This is which is called the reverse region. So PIV is the peak inverse voltage, which will be required to break the diode into its breakdown region. So it is always needed that your PIV rating should be greater than or equal to V of M. If this is smaller than V of M, then for all the reverse direction, for all the conduction, when you want this switch to be in open region, all the current will flow in reverse direction and your phenomena will be disturbed. So this thing is very important, that your PIV rating of a diode should be greater or equal to the VF for a half wave rectifier. For a full wave rectifier, the condition will be different. So what is PIV? PIV is the maximum bearable voltage which a diode should contain for the reverse bias region, and after the PIV rating, the diode will move toward the breakdown region. We know the breakdown region, that is the region where the reverse current, reverse voltage is so higher that the diode will start conducting in reverse direction. So this thing is very important. Is take a look, and I will see this full wave rectifier in the second half of this lecture. Please stay tuned and see you.